Alright, hell yeah. So we're going to go over one of the hardest chapters in material mechanics. This is Analysis of Stress and Strain. This textbook is Material Mechanics by James M. Gear. Alright, booyah. Alright, we're going to read the overview, and we'll see how far we get, because I always like to explain what's going on. So, and we should kind of just do a run-through of what we're going to be looking at. Why this chapter is hard is because we have stress blocks, you know what I mean? We have a small element. Cool. How many atoms is that? I don't know. I mean, if it's a cube, hey, let's say it's at least, you know, on a face there's going to be 4 atoms, and then, you know, maybe 8 atoms of iron. That's kind of what I like to do, and as long as you're within that, like 8 molecules of iron for steel, I think it's a good representation. So any face, you know, any small element like this could be represented as 4 iron atoms. You know what I mean? That you're trying to, you know, lengthen this way, lengthen that way, or compress. These arrows are just showing the positive direction. They can also be showing the negative direction. Or we're going to try to turn it into a diamond shape by putting shear forces on both of those faces. Okay, hell yeah. And this chapter is like, you know what I mean? We have our, maybe this is an element from a bridge, or I think the simplest is a piece of steel bar that you're pulling tension on. And if you're pulling tension on that, cool. Like every cross section that you cut this way will have that same tension. But what happens if you take that steel bar and chop it at a 45-degree angle? Well, now you're going to get normal forces and shear forces. So what we have is we want to know, like, hey, we want to make a bunch of cuts, not just at a 45, but any angle. And then we're going to try to figure out what those normal forces are and shear forces are. Cool. And so, hell yeah, so we have 3D blocks of material, and we can have a normal force and a shear force on all faces. Now, for analysis, and I think just for this chapter, and even, you know, right here, this section is going to be on plane stress, and so there is no stresses in the z direction. It's all in the x and y. And sometimes even stuff like that, you know what I mean, the forest for the trees, it's just like, hey, I see a lot going on here, and sometimes it's even hard for me to be like, oh, okay, this section's on plane stress. That means that there's just no compressive tension forces in the z direction. There's no shearing in the z direction, and so that's going to be represented by plane stress. All right, hell yeah. And then we're going to, you know what I mean, you have these diagrams, and a lot of this is going to be, most all of it is going to be in normal stress. That's this letter sigma, and we have tau for shear stress. Now, these are not free body diagrams, but this is a free body diagram. So this is probably the most important piece in this whole chapter, is showing that, oh, okay, so we have stress, that's the pressure on this face, and the pressure is this one is acting normal, excuse me, and so that might be pulling on this face or compressing on this face, pushing the face in. Now this is a shear pressure, a shear stress. Stress is in pressure, you know, units of pascals, newtons per meter squared, that's a pascal, or psi, pounds per square inch. And so I can know the force on this face. It would be the same thing as taking some tape, some duct tape, taping it to this face, and it's got some thickness into the page, and then pulling on that duct tape. Now that's going to be a force that's going to, and that force is going to be applied over that surface, and so I can know that shear stress. That's probably the simplest way to visualize a shear stress, is to tape any sort of tape, but you can just imagine duct tape on that surface and pull on that strip of duct tape. And so they're giving us the pressure that duct tape is exerting on that face. So we can then figure out how much force is on that duct tape by taking the PSI and that's going to be in pounds per square inch, pounds divided by inches squared. And so we're just going to multiply by inches squared. That's going to cancel those units, and we're just going to get the force in pounds. Same thing with pascals. That's a Newton per meter squared. I'm going to figure out the area of that surface in meters squared, multiply those two, the meters cancel, and we're just left with a force in newtons. And so if we take a look at this, this is going to, let's stick with SI units. So we have newtons per meter squared on this, and we have an area in meters squared. The secant of an angle is just a ratio of the original area. So this top surface is going to be A naught, and then when we make a slice, we're going to get something bigger than that original surface. Anytime you take a slice that's not just, perpendicular, if we're taking a slice this way, hey, our area could be A naught, but if we take a slice at an angle, that area is always going to be a bigger number, and so that's where this secant comes from. And secant, you know what I mean? Yeah, and that's the other thing. There's a lot going on with this chapter because you got trigonometry, and they're not going to simplify it for you. Secant is just 1 divided by cosine, and that should ring bells now that if I have the area divided by cosine, I always think of sines and cosines as percentages that are usually less than 1. They can be 0, they can be 100%, you know what I mean? But they're basically in between 0 and 1 as a fraction of a whole. So 0.5 is 50%. So if something is, if this area is half, just in general, sines and cosines are percentage. This is the hypotenuse, and so what we're comparing it to is one of these sides. And so, for this one, here's our angle. So the initial area would be this face. So if we go back up here, we would have the area on that face, and then we're going to take as we sweep this angle out, the area on this face is going to be a percentage of this. Now this is the hypotenuse, so it's going to be bigger. If this is the angle, this is representing the cosine, because the angle, if you put some sun-shining rays on the angle, this is going to be the sine component. Therefore, the adjacent to this angle is going to be the cosine component. And so we have, if I knew this hypotenuse, this side would be the hypotenuse multiplied by the cosine of this angle. The cosine being a fraction of the hypotenuse, that's going to be, so if we look at this, hey, let's just say this is 10 units long. This looks like 8 units long. So it looks like this is 80% of the hypotenuse. Therefore, my cosine of my angle is 0.8, or 80%. And so we would take the hypotenuse times 0.8, and that would give us this value. Now, how do we do the reverse? If I know that this is 8 units long, how do I know the hypotenuse? Well, I'm going to take 8 units, divide it by 0.8, divide it by 80%. And so 8 divided by 0.8 would then give me the hypotenuse. And so, hell yeah. And it feels like the math didn't work out there exactly how I wanted it to. But is that right? If this is 10 units long and this is 8 units long, then 10 times what is 8? And I would say 10 times 0.8. And then so if I have this, 8 divided by 0.8 is, how's that 10? It doesn't seem like it's 10. 8 divided by 0.8? Oh, yeah. So 8 divided by 0.8, holy Toledo, you know what I mean? It's hard without writing, but yeah, if I had 8 divided by 0.8, the 8 divided by 8 is 1, and then I have 1 divided by 0.1, and that's going to be 10. So hell yeah. So anyway, but hell yeah. So that was just showing, why did we talk about that? Is because secant is 1 over cosine, and if I took the area, divide it by a smaller number, that's going to give me the bigger number. So that should, so even just that should be the alarm bells that, hey, A divided by cosine, that must be a hypotenuse, from a side that's given the cosine component. So that's what you can see there. And so then this is force. This is going to be the pressure in PSI, or newtons per meter squared, and then the area of this face. And this area of this face is now that original area divided by cosine, or multiplied by secant, because 1 divided by cosine is secant. But hell yeah, I was just pointing out that, I think we can handle sines and cosines, but secants, it doesn't seem like there's any use for them other than just making something look hella technical. And I guess from a textbook perspective, hey, you don't have to do a divide by right here. You can just write everything on a single line just by saying secant. But if I see this secant, I mentally want to turn it into a divided by cosine. It just helps me mentally. And I can totally easily see that this area divided by cosine is, going to be a bigger, it's going to be a bigger number than that initial area. But now I should do two things and throw in my wheelhouse the fact that if I see area naught times secant theta, I should also know what that means. But I still don't. I would still have to just say, hey, this is area naught, the original area divided by cosine, and I kind of know what that means. But if I see the secant, I at least know to, have it be 1 divided by cosine. All right, so hell yeah. And so that gives us the force on this surface. So this is a force body diagram, and so I can find this force right here, and on this cut I can find this force as well, because from my stress diagram I can well actually, and what we're doing is trying to find the stress on this face and the shear stress. We want to find the normal pressure, the thing that's trying to compress or pull on this face, and then the shear pressure, the thing that's trying to rip it this way, or it could be ripping it in the other direction. These arrows could be negative or positive. And how we get these values for these stresses on this cut is by using a free body diagram. It says, hey, back to this original state. It's just like, hey, I've analyzed my element in a very perpendicular manner, whether this is a beam, and I know how much load I'm putting on the beam, and then I know how much shear force is on that place of the beam, and I know how much axial tension is in the beam, and so all those things I might know. And but what I'm interested in is like, hey, if I rotate the element, maybe some of those forces get bigger than I thought. And the reason we do this is because, let's take a substance like steel. Steel can be pulled upon and it can be compressed about the same amount, basically the same amount. But if it is sheared, it can only take about half the. So if I just take this force over this area, so let's just say this is a 1 by 1 inch. You can make this element as small or as big as you want it to. You don't have to make it infinitely small. You know what I mean? If you make it big, and it varies across, your bridge or something. But even if it was the Golden Gate Bridge and you're going to cut out a 1-inch chunk of steel, hey, that sounds fine. Not too much is going to go on from this 1-inch chunk of steel to the one adjacent to it. But if your beam is a 1-inch chunk of steel and you're applying forces on it, well, maybe you'd want to take this to be at least 1/4 of an inch cube, just so your forces aren't going to be changing drastically from one side to the other. Because once we do take a cube, then what we have to have is an equilibrium. If I do take this cube, what I'm going to have is that it's not, these are the pressures, but these pressures act on surface areas, and these pressures are related to forces. So even right here, they should have drawn another diagram of a force body diagram, free body diagram of a 3D cube, where right here, instead of a tau, which is a pressure, I should have an arrow that's a shear force with the letter V. And just because I think us as humans, I think we can understand forces better than pressures. And I even think there's a little bit gimmicky going on, the fact that we have sideways pressure, and it seems empirical to me. The fact that you have a sideways pressure. A sideways pressure, sure, I mean, we can understand it. I can tape this with a thing of duct tape, and I can pull on it, and I can be like, hell yeah, there's going to be a force per little area over all this, and I could have a value for that pressure. But that value for that pressure is completely different than pressures of like dropping things in the ocean or taking a spaceship to the vacuum of space. Those are normal pressures, which they're not the same. You know what I mean? And it's just fascinating that what we call, this is more of a leveraged pressure. Because if we look at what shear forces do, they're going to leverage this cube and then turn it into like a diamond shape. But in that process, they're going to lengthen this length. So if I pull up on this and pull up on this face and do the opposite on this other diagonal, it's literally the same as tensioning this on the diagonals. And so then, you know what I mean, that shows you that you have a normal pressure that's trying to tension these diagonals. And when we tension these diagonals, this box wants to collapse in. So this length decreases, and that would be the same as putting a inward force this way and that way. So just the fact that we can take a shear force and say, hey, this shear force is very much related to a normal force in this direction, and a compressive force in this direction, and this direction. And it is. This shear force is equal to those things, but we just have to orient this object at a 45-degree angle if we're going to say that. And so that's this whole chapter, is taking this cube and then just rotating it. And when we do rotate it, then we're going to then those shear forces and normal forces will vary. And so here is a diagram. So this is a special case of plane stress. In general, case of plane stress. And so plane stress. So that would be when the angle is 0, what do we have? I can't even read this. So, yeah, it's kind of fascinating. We'll have to take it one step at a time, I think. All right, so let's start reading this brutal chapter and see how far I get into it. All right, hell yeah. So we have chapter 7 is concerned with finding normal and shear stresses. So we talked about that. These are pressures. This is pressure, but it's kind of like a duct tape pulling on sideways on the face of a surface. This is compressing or tensioning that surface. All right, and so this chapter is concerned with finding these pressures acting on inclined sections. So we're going to take our cube that's perpendicular, and then we're going to make a cut through it. And so these inclined sections cut through a member because these stresses may be larger. So we kind of talked about that, and that's the case with if I have a steel bar. So just imagine a steel bar, and I'm pulling on it in either direction. I'm tensioning it till failure, and it's a 1-inch cross section. So it's a fairly thick steel bar. I always bring up this one because it's 58,000 pounds. I can put 58,000 pounds on that 1-inch square bar. But we talked about, or I briefly talked about, how steel can only take a shear force that's half. And so so as we cut the steel bar, and I don't even think they have a picture of this, but as we cut the steel bar, and I should be going back to previous chapters and finding this stuff. And so hell yeah, let's try to do that. All right, hell yeah. All right, hell yeah. So we're in the right place. So when we especially when you load wood in compression, wood can't take very much compression compared to how much it can take in tension. See these bands? Like these bands are wanting to take tensile loads. You know what I mean? You can almost think of them as stringers in a tree. But what they can't do is actually take compression. The compression is like the lignin between those bands kind of holding the tree together. Now hopefully I'm not just making, terms up, but that's kind of in general what's happening. And so that compression is way less of a value. And so what happens is that this block of wood, if you just cut it flat, all the way through, hey, it seems like you could take an infinite amount of compression if you just cut it. You know what I mean? If you just had 2 blocks of wood and you compressed them in a vise, it's like they're not going to break, are they? They're not going to go anywhere. But if you have a substantially, longer like 4x4 and you're loading it, what's going to happen is it's going to fail on like a 45-degree plane, because that's the plane where you're going to get shear forces to occur. And I mean, we just talked about how, well, I don't know, this might just be more my rambling, but we said that I say that shear forces do take a and so this is page 156. Yeah, it'd be kind of fascinating to, because this book kind of has all these shear diagrams in kind of different locations, so it's good just to kind of know where they all are. So here is the first shear diagram you're kind of come to. We have a bolt and we're going to put loads on either side of this bolt. And so that's going to be a force. That force is going to act over the surface area, or the internal area of the cross-sectional area of that bolt. So we're going to apply a load here and a load there. And that's the same, well, let's see. Yeah. So that's going to have pressures on that cross-sectional cut. And so if we take the load that we're applying and we divide it by the cross-sectional area, you know what I mean? And so what happens is that if we take that cross-sectional area is actually pointed in this direction. And so this brings up the idea of what a shear force is to a normal force. A normal force is just yanking on this bolt on both sides. And still it's going to act on this cross-sectional area. But the cross-sectional area is going to be axially, if we did cut through this bolt, the face of that area is going to be in this direction, because the perpendicular face of that area is facing, kind of this axial direction. And in tension, the force is going to be in the axial direction. So that's how you can distinguish between normal tension and normal compression. Normal forces always act perpendicular to that area, where the loads in shear are going to act, well, did I say that right? Parallel versus perpendicular. So this, I would say that the cross-sectional, this area is actually faced in the axial direction. So the loads are perpendicular to that direction. So if the area points in the x direction, the loads are perpendicular to that. Let's say they're just in the y direction. And so that's the definition of shearing something, where your loads are perpendicular to that face. And we get that same example of pressures, this quote unquote shear pressures, like lateral pressures to develop on that face. But what actually happens at this joint, and you can even see it, is like as it deforms, if you had a little square chunk, it's going to turn into a diamond shape. And so that's what this diagram shows, is that if we have these sideways pressures, these shear stresses, shear pressures, they're acting on the cut face of that bolt. And pressures times the force is going to be sorry about that. Shear pressures times that cross-sectional area is going to give us the force being applied. And so, and we just say that, just in general, this force is going to be equally distributed along that surface. So for this, that's where we get this shear average. And this is where the empiricism comes in, because you can actually not have shear forces on the surface of this bolt. The shear forces have to be internal, and they're a maximum in the middle. But just in general, this is kind of the empiricism of, like, if I took a bolt and I'm like, well, if I load it on both sides, I could do this, and I could shear it and it would break, and I could calculate the force that took, the V, the shear force, and I know the area, and I could just say, in general, if I just said this, there was going to be an average shear stress on that face. And mathematically, that is 100% right. Even if it's maxed out right in the middle, and it's 0 on the end, and it's kind of parabolic shape, and we get this shape, the definition of averaging of a function is, kind of where if the function was averaged across that face, a linear function, that would be the area under the actual curve for the stress getting distributed is going to be the same. That's going to be the same as of just saying, hey, what the average, if this is the force and that's the area, that average is going to be, the area under that curve is going to be the same as the actual area that happens under that curve. So that's where we get. And I think you need more diagrams and discussion about that, because just until last week I had no idea that this was just an average shear pressure. Even though you get into more advanced chapters where you're just like, yeah, on the surface the shear pressure is 0. And I just figured, well, that's just for, but that's for everything, you know what I mean? So when we do look at a bolt, we're just taking the average pressure. So we know, so it's empirical. We know how much load is going to be required to break this bolt in half, and we know the surface area of that bolt. So we know that the pressures, and fictitious as they may be, sideways pressures on that area, are going to be a value, and that's going to be the average. Okay, so let's take a look at what happens, because I said that if we take a small little element, which would be just taking a square right here, it's going to turn into a diamond shape. And so we have this small little square element where I showed it was, and we're going to have that load this way, that load this way. And just on this, you know what I mean? If I take a little cube of this, and I think this is where it is useful to be like, okay, let's say I have this load V, it's like 100 pounds, and then this load is going to be 100 pounds. And then I take a small little rectangle that's 1/10 the diameter of this. So cool. So then I could say that on that rectangle, I'm going to have 1 pound, you know what I mean? And so, but even that, let's say this, instead of this bolt being circular, let's say it was a square bolt. And so it has dimensions that are 10 millimeters by 10 millimeters. And so, and I have a load of still, or what should we have our load be? I'm going to have our load be 100. So we have 100 newtons and 100 newtons. And we have a square bolt that has dimensions 10 millimeters by 10 millimeters. So I'm going to take a small little box that's going to be 1 millimeter by 1 millimeter, and it's going to be in the center. And so on the surface of that box, because this 100 pounds is going to be over a cross-section of 100 squared. So we have 10 by 10 millimeters. That's going to be an area of 100 millimeters squared. That on that little box, I'm going to have 1 Newton per that 1 millimeter squared. And so, so that's what we have down here. where this isn't a free body diagram. It's just saying, hey, we have a small element. But if I said this element was 1 millimeter by 1 millimeter, the pressure on this element, and let's talk about this in pressure now, because if I said this surface area was 100 millimeters squared, and I have a load of 100 newtons, then the pressure is force divided by area. That's going to be 100 newtons divided by 100 millimeters squared. That's going to be 1 newton per 1 millimeter squared. So then I can come down here, and my little box is 1 millimeter by 1 millimeter. It has an area of 1 millimeter squared, and I know that there's going to be a force of 1 newton on each area that is an area of 1 millimeter squared. So I can now visualize this little box. Let's call it, let's see what it's called, small element of material subject to shear stresses. Those are going to be the stresses in PSI, or pressure, or newtons per meter squared. And we're just going to say they're in newtons per millimeter squared. And we have a pressure of 1 newton per millimeter squared acting on an area of 1 millimeter squared. So I could say that there's a shear force on this of 1 newton. Cool. And that is useful because I swear, I think the material mechanics books would get way better is if every time they drew a shear stress diagram where you have the pressures on the faces of an element, is that also at the same time do a free body diagram where you have a force up. And if we did that, if we had a force up on this surface, we have to, that's going to be a upward force in the y direction. So our sum of our forces have to be equal and opposite. And so we have to come over to this face and have a downward force. And if now we have, now the sum of the forces in the y direction are equal and opposite, but they're causing this thing to rotate. These two forces are equal and opposite, separated by a distance. That's the definition of a moment or a torque. And so that's wanting to cause this thing to rotate. But we know it's not. We know it's a stationary object. So we go back to our bolt. Even though we're causing this to happen, like, hey, it's not dynamics. Like, we can just pause, still have this load on there, and nothing's moving. And so that means that we have to have a counteracting torque. So if this torque is going this way, we must have to have a torque going that way. And we do that by having a force on the top of this face in that direction and one in this in that direction. And if I know the force up here is 1 newton, it also acts over a surface area of 1 millimeter, and I can know the pressure on that surface is force divided by area. It's 1 newton divided by 1 millimeter squared. And similarly, you can say that if I have a stress in this direction, it's proportional to the force in that direction. You know what I mean? It's the force will also be in that direction. Therefore, the stress over here has to also be downward. To, you know what I mean? So the even though this isn't a free body diagram, the stress diagram can, if this is upward, that has to be downward. And they have to match based on the surface areas of these. The surface areas are equal, therefore this stress down has to equal that stress up. And if these stresses are a distance apart, because these stresses are associated with the forces along that same path as these arrows, then it's going to cause a rotation that way. Therefore, I need stresses in this direction and that direction. Cool. So if we have these stresses, and now they're analogous to forces, that's why you're just going to see stress diagrams. But in Chapter 7, we're going to have to show that, hey, it's relevant that this is a force on this area. Because when we take a cut right here, what's going to happen is our area, let's say this area, what we already said is 1 millimeter squared. If I cut through a 45-degree angle, well, now this cut surface, sure, it's going to have a depth of 1 millimeter still, you know what I mean? But the cut surface on that 45 is now going to have, it's going to be the area of that rectangle, you know what I mean, into the page, is going to have a depth of 1 millimeter. and then a height of whatever this diagonal is. And so if this surface is 1, this is 1, this diagonal is Pythagorean's theorem. This side squared plus this side squared. Square root that is this length. So we have 1 squared plus 1 squared. That's going to be 2. And so we have the square root of 2 is this length. So this area would be a width of 1 and a length of square root 2. So that area is 1 times square root 2. This area is square root 2. So we have a force on this that's a shear pressure that's associated with a force. And that force is going to be equal to this pressure times this area. And so on this face, we're going to have some associated forces. We're going to have two. We're going to have a normal force on that face and a shear force. But the forces are going to be proportional to let's say it like it's a shear diagram. If I have a shear on these two faces and I take a 45-degree cut, I'm going to have a normal shear stress. I'm going to have a normal stress in the axial direction or perpendicular to that face. I'm also going to have a shear stress on that face because if I cut this 45, I could stick a stick of duct tape on it and pull it, perpendicular to the direction of the area is facing. So the area is going to be facing at a 45. If I stick a piece of duct tape on it, I can pull perpendicular to that direction. And so so that means that I have a shear stress along that area, and I have I'm going to have normal compressive or tensile stresses along that area. And even the shear, I don't know what direction is going, but those shear stresses are associated with forces. So whatever that shear stress is, I know the force is the shear stress times that area, but the area is much bigger now, and so it's going to impact equilibrium. And so hell yeah. So now here is where we just have, you can look at these as stresses or forces being applied on those areas, and it's going to, and we're going to have all these equal and opposites. So these two are going to be equal. If this is up, the other side has to be down. And that's going to cause a torque, and then these have to be countering that torque. That's the way that I would look at it all the time until you get more savvy with it to be like, hey, if I can identify one face that's up, then this face has to be towards that. If this arrow goes up, this arrow has to go towards that arrow, and these have to go away. Whether these are the shear stresses or the shear forces. And again, all arrows, whether they're the shear stresses or shear forces, are in the same direction and operating on that same location on that face. Shear stresses cause an object to make a diamond shape, but if we, this it doesn't have to be like a microscopic chunk of material. It can be a substantial, mental chunk of material. And so what's going to happen is this length is going to increase. And so if we have this material just chilling out and this length increases, well, we're going to have a axial stress along this direction. And this direction is along the 45. So along this 45, we're going to have an axial lengthening, tension. And look at this. These 2 points come together. So we're going to have compression along this axial direction. And what we do is we just make a chunk of material that's another square. And it doesn't matter like what the size of these squares are, because this is a pressure. It doesn't really matter what this area or like what the size of this element is. So I can make a smaller element at a 45 and make a smaller cube in here at a 45-degree angle. And I can say that, what can I say about it? Oh, and so we'll just have to get into that. So how to analyze that little cube at a 45 is just like we'll cut this at a 45 right here and just say, hey, this portion of the cube, we're going to be able to find the normal stress in that direction and maybe the shear stress on it. And then so the same thing, we can do that 4 times. Then, when I cut this cube right here, I'm going to be using these 2 stresses acting on areas for my equilibrium. And I would just go straight to the free body diagram. I would say that this is a force in this direction, this is a force in this direction, and when we make our cut here, I'm going to have a normal force and a shear force. And then so all those have to balance, and I can just put them in the whatever direction I want, and if I get negative numbers, I know they're acting the opposite way. And that gives me that, and then once I get those forces, I can say that those forces act over this larger area. So the definition of pressure is force divided by area. So I'm going to take that normal force and divide it by A naught secant of the angle, which is if this is a 45 degree cut, then this is square root 2. So this length is now square root 2, and our original area was A naught, and so secant theta works, because if I had so this original area, let's just say it's 1 times secant theta. That's the same thing as 1 divided by cosine theta. If theta is 45, that's going to be 1 divided by square root 2 divided by square root 2. So cosine of 45 is just square root 2 divided by 2, which is 0.707. And if I have 1 divided by that, well, that's going to give me the square root 2. And so that's going to be that's going to give you, so if I had 1 divided by square root 2 divided by square root 2, that's going to give me 2 divided by square root 2. But you rationalize the denominator, multiply by square root 2 on top and bottom, and you would get holy hell. Wait, what? What the hell? So you have so cosine of 45 is square root 2 divided by 2. The area of this is that area times secant theta. That's area divided by cosine theta. So that's area divided by cosine 45. Cosine 45 is square root 2 divided by 2. So that's going to get 2 divided by square root 2. Oh, yeah. 2 divided by square root 2. Rationalize that. Multiply top and bottom by square root 2. Now you have 2 times square root 2 up top divided by 2. So 2 divided by 2 is 1, and you're just left with square root 2. Man, but I think, I don't know. Hopefully, that's probably the worst parts of these videos, when I'm not, when I'm just, saying things from memory. But it is good to have that mental, how much stuff can you do mentally without pen and paper? All right, so this area is going to be square root 2 times that area. And that means that whatever force this is, it's going to operate over a bigger area. And so, but yeah, so you can find the normal stress, the normal pressure is this normal force divided by that area, which is square root 2, the original area. All right, hell yeah. So, and then that's just one element. So if I had a 45 degree, if I rotated this element 45, what I just found was the normal stress on that face. I could also figure out, from free body diagram, I found the shear force. And then so I can divide that by that same area, and I can get the shear stress on that face. And, once you know, so it's fascinating, because I'm even learning on the fly, is that if I know one of these shear stresses, I know all 4. See how all 4 of these are the same? We just talked about that. Same thing with normal forces. If I had a 45 degree, and I know that this normal force is now like 57, whatever, the other side is going to be the same. It's going to be 57. So it doesn't mean that I know this direction if I have an element at a 45. And so we would do the same thing. To get the other directions, I would make a cut right here. And I would cut all the way through this. And I would use this stress and then the bottom stress as my stresses. I would turn it into a free body diagram. So this is associated with a force this way, a force this way. And then on this cut, I'm going to have a normal force and a shear force. And then so just using some of the forces in the x direction, y direction, and some of the moments are going to be 0, I can find that shear force and the normal force. And then I can know what the shear stress is, because it's the shear force divided by the area. And that area is going to be basically the initial area times square root 2. And then the normal force is the normal stress is the normal force times the area square root 2. So that's basically chapter 7 in a nutshell. So now we should probably go back. We were going to talk about why, if you pull something at a 45. Yeah, I think that would be that. Oh yeah, we're ways in here. Yeah, so there you go. So when we pull something at a 45-degree angle, or just any sort of angle, one way to represent this kind of stuff is to well, let's see. So here's a bar, and if it's made of steel, it can take a tension of 58,000 pounds in the normal direction. But in the shear direction, it can only take half of that. And so if we ever get a shear force that is half of if we get a shear force, so if we pull on this, we're going to, and make a cut at a 45, we are going to get a 45-degree shear force. And if this shear force is half the value of this tension, then it could fail in shear. So hopefully I said that right. And the maximums are going to happen at 45. And so maybe we could talk our way through that as well. Because if I make a cut like totally vertical, we're not going to have any shear. And on that cut, I'm going to have a normal force, a shear force, and a moment. Moment's going to be 0, and then the normal force is just going to equal to P. I'm not going to have any shear force. But as I start to make this cut, like let's say a shallow angle, then my normal force can only operate normal to this surface. So this is the normal force, and this is actually causing it to shear. And you can see that by like taking the steepest cut possible. Let's take a cut from this corner all the way to this corner. And I think that is a very good representation of like, oh, well then along that cut. And you can imagine if you got a chunk of wood and then you make a cut like this, and then just take double-sided tape and stick those two chunks of wood together and start pulling on them. Well, hey, it'll probably fail along that double-sided tape. And that double-sided tape has two mechanisms for failure still. It can still pull apart in a normal direction, or it can shear across the tape. And this is something where I need to make more tutorials on of just like let's talk about this, because if you have this double-sided tape sticking these two pieces of wood together at an angle like that, the more tape you have, the more strength and shear that you're going to get. And and so you definitely still have that aspect where if I had tape like right here and here, and put these two pieces of wood together, and I put a force this direction and a force this direction, hey, there's very little tape that's holding those two forces in shear, so maybe I could shear it quite easily. And if you're just using tape, yeah, tape isn't very strong in tension, so if you actually just put double-sided tape to hold two pieces of wood together and pulled on them, they're not going to be very strong. But what happens is that steel is incredibly strong in tension, but it's still weak in shear. And so I still haven't found like a good analogy for something that, because tape is actually pretty strong in shear, but pretty horrible in like normal, in the normal direction. And so so that analogy, it's not very good, but it just shows you that, hey, a material can be strong one direction, but not strong the other direction. And but then if we do make this huge cut along here, is just like, whoa, well, the amount of tape that we're using, you would have to have a huge shear force like to rip that tape apart. So as we reduce that angle and kind of steepen that, what happens is that we get to a perfect place where, hey, this distance isn't too much anymore. I mean, it's only 1.4 square root 2 times this width. And then the shear force is now, this shear force is now like a 70% of P. And so that's kind of what happens. At a 45, what you're going to get is this P is going to be, let's say, like a 1. And to get there, I'm going to go this direction, the same amount as this direction. So if this was 45, this V would be the same length as N, and I would have to go 45 this way, 45 that way. And so therefore, to get a distance 1, I would have to go a distance of 0.707 and 0.707. And that's sines and cosines of 45. And so that's going to be 0.707. And if you think of that as a percentage, 70%. So now if this force is like 100 newtons, I'm going to have 70%, 70.7 newtons in shear, and 70.7 newtons in tension. And so that seems like quite, you know what I mean? But we said that the material, steel, can take a huge amount of tension. So just the fact that we're only getting 70%, that's actually like stronger in tension at this angle. But we said that shear can only take half the load. So if this is a 1-inch steel bar, you know, with cross-sectional area, and I'm pulling 58,000 pounds in tension, and let's say it can take 58,000 pounds in tension, you know what I mean? Let's just say that. But it can only take 29,000 pounds in shear. At a 45-degree angle, what we'll have is we'll have a shear force that's 70% of, so yeah, this is kind of interesting. The shear force will be 70% of 58,000, but the area that it's operating on is 1.4. So you have this is the square root, this is the square root 70, this 70% is square root 2 divided by 2. And this area is square root 2. So you have a force divided by the area. So you have square root 2 divided by 2 divided by square root 2. So that means that your shear stress is half. So this shear force is substantial. You know what I mean? It's greater than half of because that's also kind of tricky. You're just like, what? Well, if steel can only take half the shear, if I made a cut totally vertical on this 1-inch chunk, I could break it in two ways. I could pull 58,000 pounds and rip it apart. Now, it's going to rip apart like this, But still, that's going to be in tension. We're just going to say, hey, when it's going to rip at 58,000. Or I could put a line right here and put I could put a force this direction and a force this direction. On that same 1-inch area, I can only put half. I can only put 29,000 pounds. So it's just kind of fascinating that when we do this free body diagram, we get this shear force to be 70% of 58,000, which is much bigger than 29,000 pounds. So you might just be like, whoa, it's for sure going to rip apart, right? Well, the area that it's acting on is a 45-degree angle, so we get more area. But this being 70% and this being 140% more area, those two basically, like the square root 2's drop out, and you're left with half. And so the shear pressure is going to be 29,000 psi. And that's the most important part about material mechanics, is we're interested at any little point on a material. We basically have properties of that material that it can take a tension, it can, and I wouldn't call it tension. You would say it can take a normal stress. It can take a tensile stress, which is tension. Tension would be a force, but it can take a tensile stress in psi of 58,000 pounds for steel. And it can take a compressive stress in psi. You know what I mean? Putting forces on either side, compressing some sort of area. You're going to get compressive psi of 58,000. But it can only take a shear force of 20, basically half. That's kind of if you're on the safe side, you use half. It can be as high as, 60%, 65%, maybe 60%. But it can only take a psi of half in shear. And so if I put 29,000 pounds perfectly perpendicular to this 1-inch steel rod, I could shear it apart with 29,000. Now this being 70% of 58,000, I wish I knew that number. It's going to be bigger than 29,000, but it's shearing on a larger surface. So the pressures that get developed are still 29,000 psi, which is the max that steel can take. And so that shows that steel fails steel can fail at 45s, and it'll slip along 45s, even though its final failure might be straight across because it's fairly ductile. It'll still slip along these 45-degree bands, where materials such as wood, they'll just fail right at I think I was actually in the same so we had the picture of the wood right here. Sorry about that. So we have the picture of the wood getting sheared at a 45, where steel will just slip along these bands, and it'll neck down hella, and so it actually might just have a failure perpendicular. But when it deforms, if you get a load bigger than the max shear stress, these bands will form. And just from that simple calculation, these bands will form just as easily as the material pulling apart under normal stress. All right, hell yeah. So that's kind of, that would have been the preliminary chapter, that little section to read, but we'll go back and see how far we get into chapter 7. So that was a pretty decent overview. All right, so let's just start from here. So in 2 dimensions, so now we're just worried about plane stress. So yeah, it's kind of fascinating. Maybe this analysis of stress and strain. And I'm thinking we'll see if they get into 3 dimensions on this. But in 2 dimensions, a stress element displays the state of plane stress at a point at a point. So we have plane stress. That means that we're going to have we're not going to have stresses in 3 dimensions. So plane stress, it's not just normal, it's not just tension and compression stresses. That's probably where I would make a mistake and be like, oh, we just have plane stress, right? I don't have to deal with shear stress. No, you do. But things are just being pulled apart in this direction, compressed in this direction, or vice versa, and they're being stretched in a diamond shape, but all that is happening along, a 2D surface, not in the Z direction. So we have stresses, positive, negative in the X direction, positive, negative in the Y direction. Those are our normal stresses, tension and compression. Then we have shear stresses acting on tau xy. And so if we have an element, let's just grab the first picture. This is the positive X face. So this first letter is the face that this element is acting on. And we've used this throughout, If this is sigma x, We're saying like, hey, if this is a beam and this is the X direction, at some value of X along that beam, we're going to have a stress. So this is the stress on this face at that distance X. And so also, I guess if we have a beam, we're cutting it perpendicular to the X-axis, and we're going to have a stress on that face. So that's probably the more appropriate way to say it. So shear, we're going to have, on this X face, we're going to have a shear pressure that's going to be, again, it's going to be sideways pressure. And it's going to be in the Y direction. So this is on the X face in the Y direction. If we had negative tau xy, we would have, we could have two things. We could either have the negative X direction, and we could have a positive Y shear. So that would be this direction. Or we could have the, so that would be the negative X direction, positive Y shear. Or we could have the positive X direction with a negative Y shear. And so, and you can see how this tau xy is the same as this. Because positive, and what we're saying positive shear, I think it's pretty decent. Like put your axes right here. And positive shear is going to cause it to make a diamond shape in the first quadrant. So that can be one way to just quickly be like, what's positive shear? Draw your little square, and positive shear is going to make it diamond shape into that first quadrant, not any other quadrant, starting from this point. The true definition says that if I have a positive face, and so this is the positive X face, and the shear pressure is in the direction of the positive, parallel direction. So this is perpendicular direction, but we have a positive face in this perpendicular direction. And then the shear pressure, the shear stress is going to be in the positive parallel direction. So this is positive Y, and that's what we have. So over here, we actually have the negative Y direction, but we're on the negative X face. So you could, I don't know, maybe it would be useful to call this, tau negative X negative Y, just to get used to the idea of what these symbols mean. And so, but we can just say that tau xy, this would be, if you did it tau negative X negative Y, that would be negative negative tau xy. So we just have tau xy. So these are going to be the same. All right, hell yeah. And let's read this one. So we have the positive Y face in the positive X direction. This is going to be the negative Y face in the negative X direction. So we have negative, negative, and that makes this tau YX. And and I think just from, I don't know, like how are they saying this? Because shouldn't this be tau negative Y negative X? I think just by symmetry, you're knowing that from a free body diagram perspective is that this tau negative y negative x is equal to this shear stress tau yx. So I can say if this is tau yx on the positive face in the positive direction, then its opposite is the same. So these two are going to be the same. I think that might be a better way to say it. I don't know actually how they say it technically, but all right, booyah. So now we can go back to see. We didn't get very far. Yeah, we're still in the analysis. So yeah, probably for this video, I might just do the same thing and just go through, just because, bummer, I always get, that thing wants to mess up. Oh, whoops, 58, way off. All right, hell yeah, so we got to here. So we have normal stresses in the XY plane, and we have shear stresses in the XY plane. Cool, section 7.2. And then we have transformation equations. That's when we're going to orient that element at some sort of angle. And these are needed to find the stresses acting on an element rotated by some angle. Hell yeah, so that's kind of cool, just stay kind of one step ahead of the textbook. All right, from that position that we found them. So we're going to find the x, find the y, find the shear stress, and now we're going to rotate them, and we can find the new shear stress, the new shear stresses, which there's just one. I mean, if we have an element, yeah, that's the take-home point. It's like, hey, look at this. There's just one, because that's going to be the same stress on all faces due to a free body diagram. The cube or the stress element is cubic. It has the same area on each face, and the force on one face has to be balanced by the other face. That's going to cause a torque, and that has to be balanced. So that's why we only have one of those. And we just showed from something just being pulled in the x direction. What we showed was something being pulled in the x direction, nothing in the y, and what that causes is shear stresses to be maxed out at a 45. Cool. Let's read on. The resulting expressions for normal and shear stresses can be reduced to those examined in section 2.6 for uniaxial stress. See, I read that and I didn't even pay attention. So that's the hardest thing about textbooks, when you're just like, nah, I think I'm done. So the resulting expressions for normal and shear stresses can be reduced to those examined in sections. So we went to section 2.6 for uniaxial stress. That's where the stress in the x direction, I guess, the stress in the x direction was not zero. We're pulling on that chunk of steel. We're compressing that chunk of wood. But the stresses in the y direction are zero. And the shear forces are zero. But with the transformation equations at 45, you get a max shear of 2 times, or half of the normal stress. That's what we get from that. And in section 3.5 for pure shear, so I should be starting with this chapter 3 has shear forces, and with pure shear with torsion. I'm not very savvy about that as of yet. But hey, no normal stresses. So we're not pulling on the darn thing. We're not compressing it in the y direction, or but our shear stress, we are shearing like a pipe by twisting it. So we're having pure shear. Cool. And so what does this say? The resulting expressions for normal and shear stress can be reduced. Yes, so based, what is it saying? The equation that we get, as long as we throw in this is 0 and this is 0, we'll get that equation that we derived. And if we throw in this is 0 and this is 0, but this shear is pure, then we'll get the equation that we derived in section 3.5. So it's kind of that's why I probably should have started there, but we're going for it. Chapter 7, it's crazy. All right, maximum values of stress are needed for design. Yeah, and so again, maximum values. We're just interested in the max PSI in shear, compression, or tension. And we're going to relate those to how much the material can withstand. What pressure? Steel, we just said, can only take a 29,000 PSI in shear, but it can take double that in compression and tension. And so these are needed for design. And the transformation equations can be used to find these principal stresses and the planes on which they act. And I guess principal stresses are relating, I need to go back, is that just maxed? Is that just like when something is maxed out? Or is that just in the normal directions? That's what I'll be looking for to answer my question. There are no shear stresses acting on the principal planes. Oh, there you go. So these are just, the principal planes are the max normal stresses. There are no shear stresses acting on the principal planes. So there we go. So we're still one step ahead. Is because a separate analysis, we still need that PSI in shear and make sure the thing won't fail in shear, just as we showed the slip rings on a steel bar. So a separate analysis can be made to find that maximum shear stress. So that's the pressure, PSI, pascals, newtons per meter, pounds per square inch. You know what I mean? And a material can only take so much in that shear direction. Even though it is kind of a leverage direction, and we just showed that the diamond shape happens where like we are shearing it into a diamond shape, but it's ripping apart because the length of that diamond's increasing. So, and you know, mainly that's going to, and I shouldn't say that because that only happens when something is brittle, when something can't if something can elongate up to like 30% max, like steel, it's not going to tear apart like that. But chalk, you go shear chalk, it is going to fail at a it's going to fail at a 45. All right, sweet. So a separate analysis can be made to find the maximum shear stress and the inclined plane. Yeah, because maybe it acts at a 20-degree angle. Who knows? You know what I mean? So we can do that. Maximum shear stress. Maximum shear stress is shown to be equal to 1/2 of the difference between the principal normal stresses. Yeah, so maximum shear stress is shown to be equal to 1/2 of the difference between these two. So the difference means we have to subtract them. So if 1 is 0, if we just have, let's say, all tension in one direction and then no compression on top of something, just axial tension, the difference between them is just the axial tension. There is no difference. And then so the max shear force is just half of that difference. So when we do have just axial tension, the difference is the most it could be. Now that's not quite true, because if we have axial tension and then we are actually compressing the thing, this would be negative. So we have a positive and then a negative. And then the difference between them is a positive minus a negative. And then so then our shear stresses are going to be half of that. So yeah, so if we're pulling apart a chunk of steel and then we're trying to squish it in a vise as well, then we can get it to shear on that 45 much easier. That would be an interesting thing to see if we could do, like in a lab. But that's kind of what that's saying in a nutshell. And it's good to get kind of a feel for this before we actually look at the equations, because the equations, sometimes it's hard to like, pick apart different scenarios. A graphical representation of the transformation equations for plane stress, known as Moore's circle, provides a convenient way of calculating stress on an inclined plane of interest and those on principal planes. And so, so Moore's circle, hell yeah, it basically shows all those stresses. A graphical representation of the transformation equations, and I guess we'll have, do we have 3 of them or just 2? One for normal stresses. I think we have one for the normal stress in the X, the normal stress in the Y, and then the shear stress. So we'll have 3 equations, and those can be represented as Moore's circle. All right, hell yeah. Moore's circle can also be used to represent strains. section 7.7 and moments of inertia. In section 7.5, normal and shear strains, so this is lengthening or shortening in the x direction, lengthening or shortening in the y direction, and then in the xy. So positive strain is going to be, hey, the diamond shape becomes like that. If we put our element in that first quadrant of an axis, it's going to have, because positive stress causes positive strain. And normal and shear strains are studied, and Hooke's law for plane stress is derived. Cool. Which relates elastic moduli E and G. So this is the modulus. This is just called the modulus of elasticity. Now it's just a constant. It relates a pressure of like 58,000. When I say 58,000 pounds for steel, or PSI, pounds per square inch for steel, I am meaning, and it's synonymous with 0.02 change in length per length. You know what I mean? And if I have a 1-inch square bar, that's why I always take a 1-inch square bar for steel, because I know the pressure can be 58,000 pounds on that 1-inch square bar. And if I take that 1-inch bar to be 1 meter long, or 1,000 millimeters, I know it can only stretch to 2 millimeters in length. That would be 2 divided by 1,000. That's going to be a max of, that's going to be a change in length divided by length of 0.002. And so modulus of elasticity says if I have 58,000 psi over here and 0.002 for my change in length per length, E relates those. So what times 0.002 is 58,000? So I would take the 0.002, divide it by the other side, and you basically get 58 divided by 2 is 29, but dividing by 0.001 is moving the decimal place 3 places, so I get 3 extra zeros, so I get 29 million. A lot of different ways to do that, but it is useful not just to memorize that this modulus of elasticity for steel is 29 million psi, but to know that if you multiply 29 million by 0.002, you get that 58,000. And that's just the linear relationship, and that's just the equation of a line, where the same thing is true for the shear modulus. When I have a chunk of material and I stress it into this diamond shape, the lengths of the diamond don't change actually. But what does change is the angle. And so the angle changes, and it's actually related to how far the diagonal length can increase. The diagonal length can only increase by 0.002. And so we just use by geometry that the angle can only be, in radians, 0.004. And so that's the max angle change. So if I have a square chunk of material and then do a positive stress, and again, that's the positive face in the positive, parallel direction. So that's positive y, positive x face, positive y stress, which is just a force on that surface area. Then I'm going to have an equal force on the top in the same direction, and then the opposites down here, and I'm going to get a diamond shape. And when that happens, we get an angle to form, and that angle is just 0.004. So now I have, and with steel, I just said that steel can only take if it's a 1-inch by 1-inch bar of steel, I can only put a 29,000 pound shear on it on both sides. Then it's going to fail in shear. And so what this ratio says is that I'm going to have I'm going to have a shear stress, and we said that's 29,000 psi, and then I have this angle that forms of 0.004. Okay, and then so we need this shear modulus to relate those. And so if I have 29,000 on this side, and I have 0.004 on this side, I'm actually going to take 29 divided by 0.004, and oh, so shouldn't this just be half of what this would be? And I don't know, you know what I mean? It could be as simple as that. What's 29 divided by 2? I think I did this one today. It's just like something like that. It's like people want, me to use less calculators. And I think that in math, that's what can be the most frustrating, when you're just like, what's 29 divided by 2? And I think it's useful to have like 10 different ways to get there. So I thought about that today. I was just like, well, what's 30 divided by 2? That's 15. And I can kind of get there that it's going to be 14.5. So we would have, G would be 14,500,000. Don't quote me on that. Something seems a little bit fishy, but we have a shear stress is equal to the shear modulus times the amount that angle can change. And I think I'm right on this. I think the angle can change by 0.004. I just haven't, and that's just where a lot of times, just by problems, I think we do less, or I just do less shear problems and less change in angle problems due to shear, just because they're probably harder. They're just mentally harder, you know what I mean? I think shear is mentally harder to visualize. All right, so hell yeah. So these are just these ratios for those equations. And if we have no shear stress, we're going to have no angle change. In the tension direction, if I have no PSI, no stress, axial compression or tension, I'm going to get no change in length. So these are just lines that go through the origin, but their max values are a good way to actually get this constant. Cool. All right, and so we have Poisson's ratio, which is if you pull on something, it's actually going to shrink on the, it's going to shrink. If you pull on it in tension in this direction, it's going to shrink in this y direction and the z direction. And it's going to change in volume in those directions. But it's actually going to lengthen in the x direction more than it's going to shrink proportionally in the other two directions. So still, if you're pulling on something, it's going to have a net increase in volume. All right, so that's Poisson's ratio. And so this relates, so Hooke's law for plane stress relates those three things for homogeneous and isotropic materials. So this is same material, we're just, molten steel all the way through. Isotropic, no tapers. We just have a solid bar of normal shape. The general expressions for Hooke's law can be simplified to the stress-strain relationship. Oops, see, I'm spacing out. The general expression for Hooke's law can be simplified to the stress-strain relationship for biaxial stress, uniaxial stress, and pure shear. Further examination of strains leads to an expression for unit volume change, or dilation, E, as well as the strain energy density in plane stress. So hell yeah, whatever they're talking about there, that's going to be complex. All right, next, triaxial stress is discussed. Yeah, so then finally you get stresses in three directions. Then you're not just plane stress. But we start with plane stress because the equations are long enough. Special cases of triaxial stress, known as spherical stress and hydrostatic stress, are then explained. So that's what got me motivated to make this video, is because spherical stress boiled down to a pretty easy equation, and then I was just like looking at kind of where they got the equations, and it was a form of triaxial stress. And so that's why I wanted to come back to chapter 7, and I've actually never thoroughly gone through this chapter. So that's for spherical vessels. The three normal stresses are equal and tensile, while the hydrostatic stress, while for hydrostatic stress, they are equal and compressive. Cool. So, so spherical stress and hydrostatic stress. So both of those are going to be talked about. I didn't quite understand what that was saying. So finally, the transformation equations for plane strain are derived. Transformation, so it must be plane strain using all three directions. Relating strain on inclined sections to those in the reference axes directions, and then compared to plane. Oh, so still, no, plane. See, that's where it's just like, why in textbooks do I just have an assumption, and then, because it just says the transformation equations for plane strain. Plane means the xy, so just on the surface. So if this is the page, it's just the xy direction, not coming out of the page. So that's plane strain. So then they're finally derived. And for inclined sections. Are derived relating strains on inclined sections to those in the reference axis direction. So if we know the strains in the reference axis directions, we can then know the strains on angled elements. And then compared to plane stress. The plane strain transformation equations are needed for evaluation of strain measurements obtained using strain gauges in field or laboratory experiments of structures. All right, hell yeah. So I'm going to probably, I can't imagine anyone's still watching up to this point, so this might just be for my my own benefit of going through a textbook. Is this chapter is decently long, but let's say I just give myself the next half hour to an hour to just see if I can pick up simple concepts from each of these. And I could do this, without, talking into the camera, but the other aspect of this is like, hey, Can I do both? You know what I mean? Can I still not lose my cool and start just saying nonsense or just wrongness? Normal. So it looks like, what does this say? Normal and shear stresses in beams and shafts and bars can be calculated from basic formulas. So here are the formulas for stress in beams. This is shear stress in beams. Shear stress in torsion. I haven't gone over that yet. The stresses calculated from these formulas act on cross sections of the member. But larger stresses may occur at inclined sections. So that's the whole reason for this. We just showed it from pulling axially on a chunk of steel, how it might rip apart in shear. And it says we've already driven the uniaxial stress. That's the one of just ripping something apart. You know what I mean? Pulling something apart, it's going to pull apart in shear at a 45. That has to be analyzed. And then pure shear as well. And it just says at a 45 degree plane, hell yeah, that's where it's going to get real. And so in our discussion of plane stress, we will use stress elements to represent the state of stress at so we use stress elements, we're going to rotate them, we're going to use free body diagrams to when we do rotate them, knowing that the area increases, we're going to find the forces in the normal and shear directions, and then we can figure out what the stresses are. Stresses are just those forces divided by that new area. But the area did increase. And so that's why in uniaxial, you know what I mean, you can be pulling on something and you could have something at a shallow angle and it's going to rip apart in the normal direction. It's not going to rip apart in the shear direction. And you could have something hella, you could glue two pieces of wood together at a really steep angle, and it's still not going to rip apart in shear because you just have such a, it's going to be, all the force is going to be in shear along that that glued joint. But you have so much area that the force, the axial force over that huge amount of area does not make much stress. And in general, not in general, but in material mechanics, what you're interested in is those max numbers. If you get a max pressure in normal, compressive, or shear, you have to relate those to the max numbers that the material can hold. You know what I mean? The max shear, the yield shear stress of a material, the normal compressive stress of a material, the normal tensile stress of a material. Those three numbers are in books. And so that's why in our analysis, if we can come up with a plane, with an angled surface that gets a higher number, that's what we're interested in. Because it's easy maybe to get the stresses without an angle, but when we rotate that, we might realize that, ooh, we have to design for that rotated element that we just didn't, we didn't pay attention to. Cool. So that's going to happen, and those are going to be called transformation equations. What does this say? When working with stress elements, we must always keep in mind that only one intrinsic state of stress exists at a point in a stress body, regardless of the orientation of the element being used to portray that state of stress. When we have two elements with different orientations at the same point in a body, the stresses acting on the faces of the two elements are different, but they still represent the same state of stress, namely the stress at the point under consideration. Okay, so that's fairly, that's kind of a tautology. If I have if this chunk of steel is getting pulled in tension and I have this square, then I'm saying we have this and that. But then I rotate it and now I have less axial, and then and now I have a shear that's happening. And what did we say? In axial tension at a 45, I not only have tension, but I also have compression, I think. I think that's what happens. And then you have shear, where the shear force is half the normal, and then, yeah, I'll have to look that one up again. But it's what this says is that if I have a square element that just has a stress this way and a stress that way, and then I draw an element of an element, just another square, but I say it's that element at a 45. I don't have to draw it at a 45 on my paper. I can just say it's at a 45, and then I'm going to draw the stresses, shears. These two are the same, so those are the same states of stress. That's why when this is an angle of 0 and we rotate it throughout 360, we're going to get 360 different little squares with different values of the compression and tension and shear, but they're all relating the same stress at the point. That means that if we're given a problem that says, hey, this is the square stress element at a 20-degree angle, then I can find the same square with the stresses at 0 degrees or any other degree between 0 and 360. So it's basically that was a good thing to say. All right. Furthermore, we must always keep in mind that stresses are not vectors. Yes, so they're not free body diagrams. They are in the direction that a force vector would act. This fact can sometimes be confusing, yes, and they should have drawn more free body diagrams in this book, because we customarily represent stresses by arrows, and we also represent force vectors by arrows. Cool, so let's just move on because we know that. All right, so now we're in plane stress. So let's see how we do. So we're going to be in plane stress. So now we can just kind of get to those equations. And in this, we are not worried about the z direction. So we're just going to be looking, or there is no forces in the z, and there is no shears in the z. But when we go from here to here, nothing happened. We're just looking at it from a, kind of like a, if you were, a side view, a side bird's eye view. So this does have thickness, we just can't see it into the page. Now this arrow is acting, and some of the more technical books, they just use a half arrow here to say that this stress is acting at this face, and maybe that's not true. Maybe that's just for a force. If I did a free body diagram, maybe I would do a force arrow that was a half arrow. Let's see, do we have a free body diagram? Yeah, this is a free body diagram, and I think some of the technical books will just do like you'll do an arrow like this, and then just the head coming off this way. And that indicates that this force is acting on the surface. It's not acting, an inch away from the surface, and that's such a, I don't even know why I keep mentioning that, because I don't know exactly. I just saw it in a YouTube video. Someone smart said it, so I just decided to pass that on, why you might see a double-headed arrow or a single arrow. Okay, so now we're going to rotate this element, and what happens is is you can't just rotate this element and know what's happening. What you have to do is you have to cut this element. So if I wanted to rotate this element up at like a 20-degree angle, what I would do, and I wanted to know, let's just pick these two. If I wanted to know this stress and this shear stress, what I would do is I would cut this thing at a what would I do even? Oh, this is bumming me out. Let's see what they do. Okay, so they start up here. Yeah, no, I mean you have to do it that way. Yeah, so so they're going to have this angle. If I have this angle swept out, yep. So let's see what we do. So if I'm going to try to find all four of these things, and I'm going to rotate this angle up. Hey, you do it whatever way is clever. But I guess let's just make a cut. You know what I mean? So we have this angle. I'm just going to cut this element right here at a 20-degree. So let's say I only get to right there and there. This is where, yeah, it's useful to have this. If I just had a free body diagram and I said there was a force acting up on this, and then I just went to go cut this cube right here. Well, now look at this. I'm not going to have that total force acting on this new cut surface, but I am going to have the same pressure. And so when I cut this at a 20-degree angle, and it still has thickness into the board, because we still have to talk about areas, right? So it still looks like this, and I'm cutting it at a 20-degree angle. I'm going to have all of this normal stress on this face. I'm going to have all of this shear stress on this face. But on this face, hey, maybe I only have a third of this area. And so then this the force, the shear force up is going to be this pressure times a third of this area. And then this normal force is going to be this normal pressure times a third of this area. So that's what the free body diagram would look like. I would have a force down, a force to the left. I would have a force up right here and a force over that are going to be smaller. And then because I have a cut, I'm going to have a normal force in this direction that's going to be normal to the surface of the cut, and then a shear force. If you just put the convention that it's going to rotate this way, cool, whatever. But then I'm going to have those. And honestly, I wouldn't worry about beam convention when it comes to shear force, because you're trying to get this element, and this would be the positive y face, and this would be the positive new x direction. So you have to always, I would throw away your conventions from beam bending when it comes to shear on this one. But hell yeah, so then that's how you're going to find that shear force and that normal force, and we're going to find the shear pressures, which is the shear stresses and the normal stresses, because now we know the force divided by the area. The area is bigger than the area of this surface because we're cutting through this at an angle. But a 20-degree angle, it's not much bigger, and so we're going to use those. So hell yeah, so we're going to get all those things to pop up. We're going to probably get a secant of an area, because instead of taking this initial area dividing by cosine of theta, we talked about that, how that's the more, like I can recognize that more than just seeing area times secant. But like I said, I want to get better at noticing those things, so if I see this original area times secant of an angle, I'm going to be like, hell yeah, that thing's getting bigger. And I know it's going to be this new hypotenuse. All right, so hell yeah. So that's what they do. They talk about the positive conventions of shear. We already went over that. So here we go. So we have this inclined section, and when we incline the section, we have a new axis, because what's going to happen is we don't have to represent this on paper at an incline. We don't have to draw it at an incline. We can just say it's a new axis. You know, this new axis is x1, this new axis is y1. So when I draw this on a sheet of paper, I could just draw it as a rectangular square and just label my axes x1, y1. That's the transformation represented by some sort of angle. And so if you did that, you would have to write in the angle that you transformed it on the sheet of paper. But for this, I mean, hell, we're just trying to find the equations for this. We're trying to find these new stresses with any angle, knowing that we can rotate this between 0 and 360, and all our sines and cosines will jive because, you know what I mean, if I have the sine of this angle, that's going to be positive, and if it was over here, it would be positive. If this angle was more than 180, the sine would be negative, and if it was over here more than 270, sine would be negative. And so cosine of the angle is the same. So I can rotate this element as much as I want. And so we can get an equation based on, but I would never do it this way. I would actually throw in values. You know what I mean? I would throw in a value for your like tension, maybe a value on compression. You just make up your own example and then throw in a value on shear and then pick an angle. You know what I mean? Even if it's 20 degrees. And then just knowing, because that would be more useful. So if we did that, then you would come down here and be like, it looks like they chose an angle of about 30, so we can go with that. These are our given shear stresses. And what you're gonna, and they're gonna take this cut from there. So that's where they're gonna do the equations, or at least that first one. They're gonna say this angle right here of rotation is the same thing as cutting it right here. And so this is what I can make a video with pen and paper on. That's what I was starting to do tonight. Is that this face is going to give me, this cut right here is going to give me these values. Where had I come over here and made a cut this way at that same angle, that's going to give me like, I gotta, let's see. Yeah, so if I cut here at this angle, I would get these values. And check it out. If I get one of these values in shear, I know all four shears. So there you go. So I just need to do this once to get the shear. But to get the normal stress, I'm going to get the normal stress in this direction. So how do I get the normal stress in this direction? Well, I need to rotate. I need to make the cut at a, how would I do that? If I took this angle from the perpendicular, or they do that, to get this direction, I just need to take the angle from the horizontal. And that's what we started to do. We took the angle from the horizontal and did this, and what that gives us is that direction. So that initial thing that I was talking about of a 20-degree angle here, knowing that this surface area got hella reduced, but we still have a value for its pressure, we can find its force, because that's if this is force divided by area, we know the area, so then you just multiply those two. So this times area is a force, and using free body diagram, we can figure out what this shear force is and this normal force, and we know the area. So I could find those two. But yeah, because even though we have 8 things going on here, like literally, we only need to find one value of shear at using this new angle. And because, see this is Tx1, x1, y1. And let's go over sign convention again. This is our new axes, x1. This is our new axes, y1. This shear is in the x face, x1 face, positive x1 face in the positive y1 direction. This is in the negative x1 face in the negative y1 direction. Negative, negative is going to be a positive, these are going to be synonymous. So negative Tx1 negative y1 is the same thing as Tx1 y1. All right, hell yeah. So we know all, and again, the stress element has equal area, so it's synonymous with the equal force. And so a force up matched with a force down, that's like Newton's, some of the forces in the y direction are 0. that's going to cause a torque. It has to be balanced by the only other places we can put the forces, which are synonymous with these stresses, same area, and those are going to have to be equal. So cool. All right, hell yeah. And this says tau xy is equal to tau yx. We also note that the shear stresses on perpendicular planes are equal in magnitude. Oh, yeah. So, and we just talked about that, but this shear force is, this is tau yx. See, this is tau y1 x1, and this is tau x1 y1. But these are equal, but you would use, you would say the force on this face. Well, you would use Newton's forces in the y, forces in the x are 0, and some of the moments are 0. And if you take this stress over this area, and just always remember this is a cube, and so we have some sort of area. You can always make the area 1, and it literally is just proportional, where this is proportional to the force, and this would be proportional to the force. And both these forces would have to be the same. Therefore, this shear force, Tx1y1, is equal to Ty1x1. Cool, so we got that. All right, but yeah, here's the biggie, you know what I mean? Taking the stress diagram and saying, hey, this stress is over this original area, but this stress is now over a cut area. And so I think they should have taken even a smaller slice, because even visually, I can't see that this area is any different than this. That's where in these textbooks it's very useful to over-exaggerate stuff. So if we go back up here to our element and we rotate it up an angle, that's why I would only make this a small angle so you could see it a little bit better. And they just chose to, and we, to do that free body diagram, the first one that we could have done is just a cut, like I said, but they're going to take it from this vertical, and they're going to take that angle down here for theta. And so if we take that small angle of about 20 degrees, this surface, this area is no longer the original area of the cube. So this is the area of one surface of the cube. This new surface right here is much smaller. And so we're going to look at the equation for that. And so we can just do that. Like even just right here, we can read the textbook by saying, well, the force associated on this side is going to be the shear stress times the area. And guess what? The area is going to be A tangent theta. And so, cool. And how would we have figured that out? I know that this area is 1. And this is my angle. This is the sine of the angle. This is the cosine of the angle. So I know nothing about the hypotenuse. So I could say that tangent of this angle is this divided by this. And I could say that this length is associated with that area, that original area, which is 1. So I have a length of 1. And so I could say tangent of this angle is 1, or is this length that I'm trying to find divided by 1. Tangent of this angle is this length divided by this length. And then so then I'm going to take this and then multiply by the tangent of the angle to get this length. So yes, if the tangent of the angle, that's on one side of the equation, is equal to this divided by that, and I want to know this, I'm going to take this and bring it to the other side. So hell yeah. So that's the tricky thing about reading textbooks without pen and paper, and it is useful to try to mentalize that, is to be like, hell yeah, a tangent of the angle is one side of the equation. That's going to be equal to this divided by that. I want this, so then I'm going to take this to the other side and multiply it. So I have this area naught, multiplied by tangent of the theta is that angle. So we have area naught multiplied by tangent of the angle is this new little area. And even coming back up here to our cube, this area is looking like that area when we slice it. So they should show more three-dimensional pictures in this. But, I mean, textbooks, they show you just enough. And I guess it is useful. The hardest thing about a textbook is if you're not able to figure out how to read it. And you just get, you blank out and you're just, I don't know how they even got this. When tangent comes up, I don't even know how they got that. All right, so hell yeah. And then so this stress is on that same area. So we have sigma y, a naught tangent theta. And we went over that this area should be bigger than this. And so this is the cosine. I should say that this would be this area divided by cosine theta, which is this area times secant. So this is a naught. So the area of this is a naught secant theta. And the force associated with this is going to be the shear force times this. Oh, damn it. Yeah, the shear force is going to be this pressure times area. So I have tau x1, y1. That's the shear stress multiplied by the area. The area is going to be a naught secant theta. So that's what I should see right here. So this is going to be tau x1, y1, a naught secant theta. The area is this. So this stress, normal stress, same area. So we have sigma x1. This is going to be the normal stress. We want the force. We want the normal force. Normal force is stress times area, because stress is in pascals, newtons per meter squared. It's going to be force per length squared. And so we're going to multiply by a length squared, which is area. Hell yeah. So this is going to be sigma x1 times a naught secant theta. All right, booyah. And this is the force diagram. So sum of the forces in the y and has to equal to x. So if we sum the forces in the y, here's a y, here's a y, and this has a y component. The y component on this would be secant theta sine theta. That would be secant theta, which is 1 over cosine, times sine theta. This just becomes, so this has a tangent component. So that would be tangent of this angle. This has a y component as well. That is, and I think the hardest thing is to, especially when they rotate the angle close to 45, you're just like, well, I can't see it no more. But as we rotate this like a barn door, this is like a almost like a turnstile, where you can consider this like a door that's like a turnstile, where like it's rigid. It's a rigid corner. So if I rotate this down to here, it's going to also rotate to there. Cool. And then the same thing with this. This triangle is going to be in the same direction as this. So let's rotate this all down, and then this triangle disappears, and we just have a vertical line. As I rotate this axis up, a shallow angle, like real shallow, this opened up a shallow angle, and then therefore this angle opens up a shallow angle, because this face is parallel with that line. And so hell yeah. So this angle right here, and then if this is the arrow that I'm interested in, I guess I could just use this angle, right? But sometimes it's useful to be like, I could draw a vertical up on this arrow and say, hey, that's the same angle. And yeah, and so if I did that, a vertical up right here, because you'd have a nice little Zorro, or you'd have a perpendicular line and then a perpendicular line. And so that's the definition, that this angle is the same as this angle. And if I drew an angle and a vertical line right here, I could totally see that this vertical part would be the cosine. If this angle, draw some sun shining rays, this is going to be the sine component, and this is going to be the cosine component. I could also just use this angle, and I should get better at that. Just because this is a vector, it doesn't matter if it's going in this direction. I could equally say this arrow is going the other direction, and then therefore the vertical component is the cosine. So this vector, I can use this angle. So hell yeah. So the vertical component is secant theta cosine theta, which is just, so those cancel. Hell yeah. They don't go into the sum of the, no, they do. I think they go into the sum of the forces in the y direction and the x direction. So let's go over that. So the forces acting on the left hand and bottom faces. Anytime they get technical in a textbook, you know what I mean, go to the figure. So the forces acting on the left hand and bottom faces can be resolved into orthogonal components acting in the x1 and y1 directions. Whoa, 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 whoa. The forces acting on the left hand and bottom faces. All right, I don't see what they're talking about. I thought they were talking about these two. I think they're talking, if they're saying the x1 and y1 direction. Oh, got it. So we actually, so forget all I said about the forces in the x and forces in the, you can do it that way. But what we're more interested in is we're interested in these resultant forces. So as a whole. So I want to solve for this force. And so what we do is we have to, our sum of the forces in the x and y direction are these new x and y directions. So that's what they're doing. So this is the new x direction. So the sum of the forces in these directions have to equal 0. So let's go through that because it is useful. So this is just going to be positive. So this is going to have no angle adjustment. It's just all in the x1 direction. So let's do some of the forces in the x's first. And this, I'm going to use this angle, and I'm going to have, it's going to be a negative sign. So we have tau xy a naught sine theta, but it's going to be negative. So let's go pick apart that one, and let's see where we find it. So we have tau xy sine theta x. Oh, we got to multiply it by the area. Yeah, we had it. Tau xy a naught theta, and we want this component. And that's going to be negative. It's the sine component in the negative x1 direction. So that's that value. Let's do this one. This one, our angle. So this is going to be a little bit harder because our angle is, if you took our angle off this is going to, I always do, if I have a right triangle, I do this, if this is the angle theta, do some more water. I always like to think of this angle as phi, because it's just 90 minus that. And so let's see if we can use some of our trigonometry skills. Because even this one, I kind of want to go off this angle. I don't want to go off this angle. And so how would I do that? Well, yeah, Let's see. Yeah, I'm kind of stumped. So that's one thing that I'm kind of lacking in. Is just like, how do I get this component in that direction based on that angle? And how do I do it fast as hell? Holy Toledo. So if I went off this angle, this would be, yeah, let's go off this angle. Let's do it. And then this would be the sun, like the sun shining, if this is the angle, the sun shining rays, this would be the sine component. And that would jive. If I had sine of phi, and I just got to know that, hey, sine of phi is the same thing as cosine of theta. You know what I mean? If this is 90 minus theta, yeah, so I just, that's one to throw in your playbook to be like, hey, if I have, because then I don't have to do a whole lot of anything. I just like, hey, I know this angle's phi, and it's going to be the sine of phi, which is the cosine theta. So this component is going to be the negative direction, negative tau yx a naught tangent theta cosine theta. And tangent theta cosine theta is sine theta, because tangent theta is sine theta divided by cosine theta. And then I'm going to multiply it by that cosine theta component, which is the sine of phi, but, it's the, what are they, complementary angles. So sine theta divided by cosine theta multiplied by cosine theta. So this just becomes sine theta. So I have negative tau yx a naught sine theta. That's what I should see down here. Where do I see it? Tau... Oh, and they just do it like this. So they don't even simplify. They could have simplified it, but probably thank God they didn't. You know what I mean? Sometimes if you simplify too much in textbooks, I don't even know what you're talking about no more. Okay, so that's... So what did we do? We did two of them. We did this one and this one. Now let's do this one. Are we going to have an issue with this? No, this is in the same direction as this one, so we can use this angle again. And this would be the sine component, and it's going to be in the negative direction. So we're going to have sine theta, tangent theta, sine theta, which is just going to be tangent theta, sine theta. So this is going to be negative sigma y a naught tangent theta sine theta. Is that what we get? That's what we get right here, and that's going to be in the negative direction. Hell yeah. And then, so this whole section right here is just taking all of these four forces and then putting them in, well, the first part is putting them in the x direction, and then we can go put them in the y direction. And I got to take a little break. Oh, I don't want to. I kind of just want to click this one and done. So we'll see if I can hold it out. All right. So this angle, same thing. I'm going to come in here and say this is phi, and I want to know this angle. So I want to know the sine of phi. So this is going to be the cosine of theta. Hell yeah. So this in this direction is going to be negative sigma x a naught cosine theta. Sigma x, yeah, there we go. Sigma x a naught cosine theta. And I think we got them all. Oh, and then obviously we have the two originals. We have this force, which is in the x direction. And that's the only one. This was not in, this has no component in the x direction by definition. All right, so hell yeah. So that's, and in a similar manner, we're gonna tag the ones in the y. So let's see if we can, like, obviously this is in the positive y1 direction, and let's see if we can just see which ones they're doing. Now they're doing the sigma x. So where is this sigma x in the y direction? Well, let's come in here to our triangle, and we're gonna say, well, I know this is phi, so I would know it's the sine of phi, so it has to be the cosine of theta. So this is going to be sigma x a naught cosine theta, and it's going to be in the positive y direction. Ooh, we busted that one up. Oh, no. This is the x. So, yeah, right here. Sigma x a naught positive. Oh, we messed up the... What? I thought we had this. So, if this is our right triangle, this is theta. That means this has to be phi. I want to know the vertical component, which would be the vertical component of this, if this is our angle, phi. Oh, am I kind of just messing up how this works? If I have this angle... Oh yeah, I think I'm fundamentally messing up how this works. Because if I had this, yeah, this is tripping me out, and hopefully I didn't make a mistake on the other ones. I don't know why I'm losing it right now, but it's just because this is a if this is the right triangle, this component is in. I want to know the component in this direction. Okay. Oh, so I need to make this into the hypotenuse. That's what's tripping me out. If I made this into the hypotenuse, and then took a right triangle to this area, right there, then this would still be phi, and this would be my hypotenuse. And I would want to know the cosine of phi. That's the one in this direction. Holy hell. Which would be the sine of theta. That was brutal. And so so again, if I took this arrow to here, and then I have to turn this into a hypotenuse if I'm trying to take a sine or cosine of it. And so I turn this into the hypotenuse. That means I take a right triangle down to this point, and now I have this as my right triangle. I know that this angle is phi. This is the 90, so this is theta. So I could just say, hey, this is theta right here. Here is my hypotenuse, and I want to know the component in this direction, which is the sine of theta. And hell yeah, and this is going in the direction of the positive y. So sigma x a naught sine theta. Whew. Sigma x a naught sine theta. Hell yeah. All right, so now the next one is tau xy. Let's do that one. So, well, there's two of them. So let's see what they'll probably do this one first. And we want to know its component in this direction. So this is theta. So this is going to be an easy one. It's going to be in the negative direction. And we want the cosine of theta. So negative txy a naught cosine theta. Negative txy a naught cosine theta. All right, so we got our first three terms, the last two, sigma y. So now we're going to come down here, and we're going to figure out what component of this is in this y1 direction. So how should we do this? I'm going to take this up to this triangle and say, booyah, this is the angle. And so then if this is the hypotenuse, I'm just going to take the sine of this angle. Sorry, if this is the angle, and this is my arrow, I want to know, what the hell do I want to know? I want to know the cosine component. Yeah, so if I take this as my triangle, this would be the right triangle. This arrow has to be my hypotenuse. And then take that right triangle right there. This is my angle theta, and I want the cosine component. And it's going to be negative. And so tangent theta, cosine theta, but you could simplify this and just turn it into sine theta. Because sine theta, cosine theta is tangent, multiplied by cosine theta, the cosines would cancel. But they're probably going to do it, tangent theta, cosine theta. And it's in the negative direction. So sigma y a naught, tangent theta, cosine theta. Negative sigma y a naught, tangent theta, cosine theta. And the other thing that I'm improving on is just saying what it is. There's a real tendency just to like not want to say technical jargon. And so, I don't know, I'm just trying to get used to that aspect. And so that's what we got there. And so now the shear one. So now we're doing this one. And it said this one was in the negative direction. It didn't seem, no, it's positive direction. I don't know what I was looking at. Probably looking at this one. Didn't scroll down far enough. So yeah, so at least we know this is in the positive direction. We know it's like, you know, this value, but only a percentage of it. So we have tau yx a naught tan theta. And so right here we have tau yx a naught tan theta. And you can just see that this is the percentage of it. It's a sine of theta. So even if we go here and we say that this is theta, and let's just say this is my hypotenuse, it just means that this is the sine component. And if we said that this was the hypotenuse, this would be the sine component. So yeah, we're just trying to look. Well, holy hell! Let's not do that. So here's our arrow, and we're going to use that same strategy of saying, hey, this is phi, and if I knew this was phi, I'd want to know this component because that's in the y1 direction. And so this angle, this would be the sine component in the perpendicular because the sine component, sun is shining on the sinin. And if this is the angle, it's the cosine component. So cosine of phi is the same thing as sine of theta. So there you go. So we have positive tau yx a naught tangent theta sine theta. And we did it. Hell yeah. So that's probably the hardest part. And this is worth going over. Because if you've never done the force forces, free body diagram, on the element that you've rotated and figuring out. And again, like you can make this angle at any, any place that you want. Because you could do the same thing. It's just a fact that if you do it in the x directions, this x direction, like, hey, we solve for, well, let's see what we did solve for. So using this force diagram, what we have solved for is this value. Like, we know these. We know those four. What we don't know is this. And we don't know this. And once we do solve for this, this is the force on this area. So we can divide by this area, and then what we'll get is the shear. We'll get that value. And we'll do the same thing for this one. If we can figure out what this force is from the force equations, some of the forces in the x1, y1, and the moments about O are 0, and you would take the moments probably about these 2 points, or where would you take the moments? Probably about, I don't know. Yeah, it's fascinating where you would take the moments on this one. Maybe you don't even need to. But anyway, yeah. So then you would find this force, and you would know it's acting on this area. So then you can find the stress. Then you can find the stress value. And we just know that if we find the stress, if we find this stress and this force, I mean, if we find this stress, we know all 4 stresses. If we find this, I call this a force. If we find this normal stress, I know that normal stress, because they have to be equal and opposite. And that's a free body diagram thing too. This pressure operates on the same area as this pressure, and it's synonymous with a force in that direction, and those forces have to equal. But this can be different than this stress y1. So this, but once we know one of those, then we know both of those. All right, so from here, this is going to give us sigma x1 and the shear, but it's not going to give us sigma y1. I don't think so. I think we have to use another equation for that. Oh, but it probably does something technical, but you won't have to do anything technical. You would just find the other cut at the same angle on that face, and then find the stress in the sigma y direction. So let's actually see how they. So here's the 2 force equations, and then you just put them together. You know what I mean? So so this has something we don't know. That's sigma x1. We do know sigma x. We know sigma y. We know tau yx. We know tau xy. We don't know tau x1 y1. So those are the things we're trying to solve for. Sigma x1 and tau x1 y1. And I guess they're just showing that this is tau xy, this is tau yx. These are equal. So then if these are equal, then we can add those 2 components together. And again, this is tangent theta cosine theta, which is just tangent. This is just sine theta. So this boils down to sine theta. We have 2 of these. So now we have minus 2 tau xy. So we have minus 2 tau xy a naught sine theta. So that's what we should get here. So we have 2 tau xy sine theta. Well, why do we get cosine theta? Yeah, this is just sine theta. Oh, because we're trying to solve for this x1, which is divided by cosine. So by the time we get everything to one side of the equation, so yeah, you're going to get that 2, what I just said. Now here, you're going to get a sine squared divided by cosine. And keep that in mind, because we're going to multiply by cosine. That's going to go away. Over here, we're just going to have sine theta on both of these, but we're going to multiply by cosine. So we're going to pick up a cosine. And here, we're going to get another cosine. So we're going to have cosine squared. And so, so hell yeah. So you're going to get the cosine squared on that x term, the sine squared on that y term, and then you're going to pick up a cosine on this term. And we just know that sine squared cosine of the angle is 1. And so, well, no. I don't think you can do that. It would only be, you can only do that if you can factor those things, but you can't. But they do use, no, that's it. That's the equation. So booyah. And then on this second one, let's see what they do. They're trying to solve for this. And then, and the other thing is we had an area here. You can just piece that out of the entire thing. Everything's a function of the area. So then this, your area disappears. So you get stress is equal to this. But this equation now is just kind of meaningless. The second you get a technical equation, it is useful for your 10 rodeos to actually go through this whole process and solve this equation 10 times for yourself. If you don't, and I haven't, but I at least have done it probably once. So there you go. But doing a problem, that's kind of my new MO, is just like, especially if you want to get good at the proofs. If the problem statement says use this equation, well, prove the equation technically about 10 times before you're just like, yep, I've done that rodeo. Don't need to do it no more, and you can just go for this equation. But in this form, it's just like nothing. Yeah, it doesn't look familiar at all. So let's solve for tau x1, y1. And we still haven't even solved for sigma y1. I don't know if it says just do the same thing over again. That would be kind of fascinating. Let's see where it actually says sigma y1. As an important observation concerning the normal stresses can be obtained from the transformation equations, as a preliminary matter, we note that the normal stresses sigma y1 acting on the y1 face of the inclined element can be obtained from equation 7.4a. Let's go there. So it's this equation. So this is the transformation equation. So now we got to read this. What the hell is this? Transformation equations for plane stress. Equations 7.3a and 7.3b. Those are the ones we've just came up with. On an inclined section can be expressed in a more convenient form by introducing the following trigonomic identities. So here's 3 trigonomic identities, and so cool. So they just made them simpler, and but when they did that, they introduced a sigma y. So holy hell. So that sucks. You know what I mean? I'd have to spend a whole day to figure out how just these trigonomic identities, how they can pick up a sigma y, because these equations. Oh no, this equation does have a sigma y in it, and why is that? When we have a sigma y right here. Did I just space on something? Yes, I'm sorry. So we do. We have a sigma y. No, that's what I wasn't interested in that. Okay, yeah. So we have a sigma x and sigma y. Those are given. What we don't have is that sigma y1. But when we do these transformation equations, we get this. And so cool. That's it. We get something that's maybe more useful, simpler. So why can we pull out a sigma y1? So let's now go back to seeing where we can just express that. Summing the expression, so we can, the result is the following equation for sigma y1. All right. So that sucks, because I think you should just do another cut. I don't know I don't know, like, from my perspective, I don't see a magic wand that just says you can get sigma y1 from that equation. I think, like, from my perspective, I would need to make a cut in this direction, still with that same angle, and then solve for sigma y1. And cool, I would still use those trigonomic identities to simplify that. And cool, I would get sigma y1, but I think there was a lot of hand-waving between that section. But maybe there is. Maybe there's something that just is obvious, that it's like, if you know sigma x1 in this form, it's very obvious. So we have a plus, and then we have a minus and a plus, and here we have a plus, minus, and we have two minuses. So it's different. So this is, and the fact that sigma x1 and sigma y1 are related in this way, and I guess it's, oh, here it is. So here it is. Yes, because sigma y1 acts on the, so thank goodness, because it's good to ponder questions before, yeah, that textbooks are very difficult, but it's because sigma y1 can be expressed as theta plus 90. So if we make our cut at an angle of like 90 plus theta, you know, I mean, that's the identical thing of just taking our cut at if this. So if this is theta, we're gonna come 90 and then plus theta. So that's going to be our cut. And so let's just pretend our cut's right here. And then so we have the bottom surfaces are known. We know a portion of this surface, and now our area is bigger, and we can use the free body diagram approach to figure out sigma y1. So they just use trigonometry, and I buy that. So because sigma y1 is just theta plus 90, we can go through, and so let's do that, because we can take this equation and throw in theta plus 90. And so, yeah, it's fascinating. I did this, and I think I am going to, well, man, I don't want to take a break. I kind of want to just do this in one go, but I think, oh, bummer. I think this is probably where I'm going to end, though, because we have these transformation equations. Now you can know that the stress is might be a different value, it might be a max value, and that's basically all you need to know for like this part of the chapter, and then you're just going to get into more of the nitty-gritty details. So if I can, been drinking too much ice water, but I don't want to have to edit this video, you know what I mean? It just requires like 2 hours to like pop through online or whatever, right? Instead, just post it. Even though these are lower quality, they can actually post pretty fast. Okay, so what I would do is, because we're choosing an angle of, let's say, like 10 degrees. And let's choose an angle of 5 degrees. So we're gonna say, hey, my slice is only 5 degrees, and then I'm gonna pick up a different value for this sigma x1, tau x1, y1, and then sigma y1. So that's kind of what we're gonna do. And I know this equation is for sigma x1. And I know that sigma y1 is just this angle plus 90. I think it is useful for me to say, hey, let's throw in a value. First, let's throw in a value of 0. If theta is 0, this is going to be cosine of 0 is 1. So keep that in mind. But let's say I throw in a value of 5. Okay, 5 degrees. I'm going to get something pretty close to 1. But let's say I throw in a value of 90 degrees. Well, cosine of 90 is 0. But let's say I throw in a value of 90 plus 5 degrees, so 95. What's cosine of 95? Now, you might have to do like an axis and be like, hey, if this is my angle and I go to over here, I'm going to have, well, I'm going to have a negative value. So if I throw in a cosine of 95, this is going to be and we need to go to the simplified version. So sorry about that. So let's go here. And I'm going to throw in an angle of 5 degrees. 5 times 2 is 10. And I'm first going to start out with 0 degrees. So cosine of 0 is 1. And then I'm going to go cosine of 10 degrees, basically almost 1. Doesn't really change. Then I'm going to go cosine of 10 degrees plus 90. So my original angle, I'm going to say theta is 5. So I'm going to go 5 degrees plus 90. So that's going to be 95. And then 95 times 2 is 100. See, I almost messed up. So if I'm going to transform this at 90 degrees, I got to go theta plus 90. If I throw in a value of the angle as 5 degrees, it's going to be 5 plus 90 times 2. That's 95 times 2. It's 180 plus 10, 190. So if I go on my axes of 190, then my cosine is going to be just a negative value. So at that, I don't think I had to get too technical with that. So this becomes negative. So if I throw, so this just term becomes negative. The sign the same. Let's see if I can just do a 0 value. If I throw in 0, I don't know if I want to do, yeah, I think I can do that. So if I throw in, no, I think it's useful, because if you throw in, yeah, you need to throw in at least a slight positive, because let's say I just threw in 0 for this. Cosine of 0 is 1. And then let's say I threw, and I took 0 plus 90. So its cosine of 180 is negative 1. Okay, so that jives. And then, so how about this sine? Would that also work? Sine of, I don't think this one works, because if I had sine of 0, that's 0, and then sine of 90 times 2, sine of 180, that's also 0. So it's useful for this one to throw in a small positive value. So we'll throw in 5 degrees, and if I have 5 times 2 is 10, sine of 10 degrees is going to be a positive. And then let's do 5 plus 90, that's the transformation, is going to be 95 times 2, that's going to be 190. So I have an angle of 190. My sine component is going to be negative. So there you go. So this becomes negative, and this becomes negative, and we have sigma y1 as a, so we have negative, negative. So that's where this transformation comes from. But it's just fascinating in textbooks. They just, you know what I mean? That's not much of a bone to throw you, and then they just do that. So anyway, I gotta be done. So thanks for joining me, and that's a video.